In this video, we are going to take a look at a related rates problem. So let's jump right into it. Here we have a trough is 12 feet long and 3 feet across the top. Its ends are isosceles triangles with altitudes of 3 feet. Water is being pumped into the trough at 2 cubic feet per minute. How fast is the water level rising when the depth is 1 foot? All right, a lot going on. Let's draw a picture. So we have this trough. It's 12 feet long, 3 feet across the top. The ends are isosceles triangles. We have something that looks kind of like this. Sort of like that. I'm going to try to clean it up maybe a little bit. So this is our trough. What do we know about this trough? Well, it's 12 feet long, so this is 12. We know it is 3 feet across the top. Its ends are isosceles triangles with altitudes also 3, so that length is also 3. We have water that's being pumped in. So you have your water level. Let's call that some value h, the height of the water. Yeah, and so we want to know how fast is the water level rising. And we know it's being pumped in. It's being pumped in at some value of 2 cubic feet per minute. So that is a volume. So what relates our volume? So we have volume of this. The volume of water is going to be, all right, so we have a triangle here. You'll have the height of that times the base, so it's 1/2 base times height. Times that length of 12. So 1/2 base times height. But what is the relationship between this base right here, right? So between that base right there and this height right here? All right, so let's think about the end of that trough. So you have this triangle. You also have this triangle. How are these triangles related to each other? Oh, they're similar triangles. So the ratio of this side to that length should be the same as the ratio of that length, h, to this side. So 3/3 is equal to h over b. So the height and the base should be the same. And so we use properties of similar triangles. So this volume we could rewrite as 1/2 times the height squared times 12, so 6 times the height squared. That is our volume. So instead of having two variables over here, we went ahead and solved for this variable, the value of this base, the width of the water at any point in time, with respect to height. All right, now we're going to take our derivative. dv dt is 12h dh dt. We know that dv dt, the change in volume, is 2 feet. It's going up, is equal to 12 times h, the height. We want to know when that depth is 1. Divide both sides by 12, and so we have 1/6 is dh dt. So dh, the change in height, the change in the depth, is approximately 0.1667. And the units we have, these are all in feet per unit of time. Our unit of time is minute. So feet per minute. And that is our final related rates problem. We will see you next time.